Hello, welcome everybody, and thank you for being here today to attend to our webinar on Power Transformer and our ultimate global transformer monitoring solution. My name is Marco Piga. I'm a regional sales area manager of Altanova Group. Together with me today from Bologna, Italy, my colleague, Mr. Mirko Melloni, who is the chief or project management, and he will help us to reply to all your questions during the presentation. Before we start, few tips on the GoToWebinar platform. During the presentation, your microphones will remain muted, but feel free to do your question using the dedicated panel questions in GoTo platform. You can start also immediately, and we will try to answer to your all of your questions during this presentation. If not possible, surely you will receive a reply by email in the next days. You will find also another panel on GoTo handouts to download the PDF of the webinar and some other documentation. Another tip, video and presentation will be available also on our website under the Academy section in a couple of days from now. Looking to the agenda, after a quick introduction about Altanova Group, we'll have the most important question, why monitoring of power transformer, then an explanation of our brand new GTMS, so the platform for a global monitoring system, then partial discharge testing and solution for PD, case study, and in the last 5 minutes, a question and answer from this session. Altanova is a leading company in the field of advanced condition assessment technology. Today is a group of 3 strong and long experienced companies in the market of testing equipment, services, and the monitoring solutions. These companies are ESA, Techim, and Intelliso. Nowadays, we are able to provide a broad portfolio of solution covering the full range of tools for any practical application in electrical systems. In this picture, you can see solution for CT-VTs, power transformers, cables, surge arresters, ground grid substation inspection and testing, GIS rotating machines, and then circuit breakers, switchgear, relays, and also overhead power lines. You can see in this slide the 3 pictures of our headquarters. The first one in Taino, founded in 1938, ESA. Then in Bologna, we are connected from Bologna, founded in 1999 as Techim headquarters. And the last acquisition in Andover for Intelliso, founded in 2011. So we have basically 3 headquarters, 2 in Italy and 1 in Massachusetts, USA, and also 8 regional offices located in France, Germany, Emirates, India, Singapore, US, Panama, and Brazil. We have up to now more than 100 distributors. You can have and got a list from our website under local distributor section. We have also a service team worldwide, located mainly in Italy, in Germany, US, and India, to provide online, offline test and commissioning to all of our customers worldwide. We have also 3 R&D departments for online and offline solutions, and today about 130 employees. Regarding the solutions for transformers, Altanova can offer a test kit for offline test, partial discharge test in terms of services, but also equipment and global monitoring system. In this presentation, we will see more in detail the new global monitoring system, GTMS, and the section dedicated to the partial discharge. After this very quick introduction, we would like to know each other a little bit more. Then let me launch the first poll. Basically, what we are asking is, which is my main responsibility? I'm a transmission distributor system operator. I'm an asset manager or a substation engineer. I'm involved in the design on OEM sector or a project engineer or others. Good, look that you're voting. Then other 5, 4, 3, 2, 1. Okay. These are the results. So we can see that the majority of you is in a harder segment. 20 is asset manager, 8% of transmission distribution operators, someone else in OEM sector. Then thanks for your replies. Then let me close a second here. And the following section are dedicated, let me say, to all of you, all the transformers operators, and I hope you will enjoy it. So regarding our question, why monitoring of power transformer, you can see here some videos. Let me launch the videos. Probably too noisy. Power transformer are one, as you well know, of the most critical and expensive assets, and take a very long time to be replaced in case or restored in case of failure. Transformer failure is a very real concern for the owners, the operators, and the manufacturers. On the left, I would like also to share with you some interesting figures. These figures are from a middle report on November 2018, and you can see a lot of percentage. These are the concerns of the major failure modes. We can see here almost 20% for lack of maintenance, other 19-20% about the aging of the transformer, other 18 for electrical failure, and then overloading, the quality of the equipment, or weather condition, mechanical failures, and other aspects. Here another study from CELG from Brazil, now is Enel, with some important figures regarding the failure mode. This data has been collected for almost 30 years from hundreds of transformers with problems. And we can see that almost 50% of the failures are represented by windings or bushing failures, while tanks and the cooling system add an additional 15% approximately. The reason of the failure of the windings are basically due to the lack of insulation inside the tank. And with this webinar, we want to share with you our experience in dealing with these numbers. Let me distribute for another quick poll regarding this question. How concerned are you about transformer failure? Are you very concerned? Are you somewhat concerned, or somewhat unconcerned, or totally unconcerned? Few seconds to complete your pool. Other 5, 4, 3, 2, 1, and we can close the pool. Here are the results. So 63% of you are very concerned about the possibility to have the failure, 30% somewhat concerned, and only 10% somewhat unconcerned. Zero unconcerned regarding the status of the transformer. I can hide. And I can say that these results are that we got today are very aligned with other independent surveys and study, where we can see that more or less 80% of the transformers operators are concerned about the transformer failure, and they expect to have a problem in the next 5 years. So the good news for all of us is that many of the causes of the transformer failure can be largely within the operator control. A complete, in this case, monitoring system avoids the most part of the transformer failures, due basically to the lack of maintenance, but also aging, electrical failure, or overloading. And last but not the least, a complete monitoring system helps also the transformer operators to increase, as you can see here, the profitability, the reliability, and the safety, not only of the transformer, but for the entire substation or installation. So we are ready probably to see a little bit more in detail the GTMS, our brand new global transformer monitoring solution. Starting from this graph, we have seen in this pipe the components that are responsible for the failure modes. And we have seen a large number of failure, different cases. In order to maximize the, let me say, the mitigation of the risk, we have to consider to monitor multiple factors, like, for example, the oil temperature, tan delta, degradation over time, the values and the trends of the gases, the activity of partial discharge, and many others. And it is really essential to monitor the installation system, the working condition of all the components, in order to reduce the cost also of the transformer's life cycle and to guarantee the reliability and durability of the asset. And this is exactly what is the aim of the Altanova GTMS, so the global monitoring system for transformer, capable to address more or less 80% of the failure modes in power transformer. In this slide, and you can see the list of the parameters that can be monitored by the global transformer monitoring system. Basically, we have 4 modules. The first one is for, and we call it generic transformer parameters. So you can see that we can monitor line currents, oil temperature, core and winding temperature, cooling system, and hotspot temperature and loss of life. But also bushing monitoring in terms of absolute and relative tan delta, the capacitance values, the leakage current, the degradation of tan delta, and other parameters. These modules can be combined based on the customer requirements. And you can see also here the other 2 modules. One is dedicated to the DGA analysis. We can have from 1 gaze up to 9 and more gazes according to the client specification and requirements. And also we have the last modules for partial discharge monitoring in order to detect, identify, and analyze the partial discharge activity and the trends inside the transformers. And for all these measurements and parameters, we have a warning and the alarm thresholds that we can set in the system in order to highlight problems and to communicate problems, in other terms, alarms, to the SCADA system, in order for sure to prevent failures. Here you can see a picture with all the 4 modules installed, the generic transformer parameters, bushing monitorings, the solvent gas monitoring, and partial discharge monitoring. The modules can be used all together for a complete system, or can be used individually or in a combination. You can see here some sensor. Here is the part at the top adapter. Sorry if the font is too small. That is normally installed on the bushing side. Then we have tan delta sensor, some other sensor for partial discharge detection, like a UHF spiral antenna, then a DGA unit. On top, you can see GTMS hub, where we can have all the acquisition units installed in a box with IP66 or 68 IP degree. On the right, the unit that we use to collect data from the sensor, and we have basically 4 different type of acquisition unit. The first one is PD scope for partially charge. Here, EDS Mark III for generic transformer parameters, a unit dedicated to tan delta acquisition, and for sure the DGA. You can see here also a central unit where we can install our T-SCADA. Is a software platform that can collect all the information coming from the transformer and other assets installed in the substation. In this slide, you can see the front panel of the EDS. EDS, our expert system for transformer parameters and for tan delta. You can see here different slots, different cards. Each card can be configured according to the application requirements. You can see here some example for PT100, PT1000 for temperature measurements, or current measurement for line currents for fan, for example, or pumps, and for I²T calculation, or other kind of analog or digital input. We have also a section dedicated to communication, and you can see here at the beginning, the first slot. We have in this case 2 fiber optic that can be used for a ring configuration up to the server, and some other accessories. This is another example, not only for the EDS, but for the hub, for the GTMS hub, with also the tan delta unit. This is here inside the red circle. This unit is capable to monitor up to 12 channels. So basically 6 bushings and 6 CVT. We have in this case 2 configuration. One is basic configuration, and we have also the advanced configuration. The big difference is that for basic configuration, we can detect the relative tan delta values and some other parameters. With advanced configuration, we can have the absolute tan delta value and some other important features. Sorry. Here an example of the basic configuration starting from on the left. You can see here with 3 bushing only or 6 bushings connected to the capacity tap using a dedicated sensor up to the EDS unit. And in these other 2 cases, the advanced configuration, when we have 3 bushings plus CVT as reference, or on the right, again, advanced configuration with 3 bushing with other 3 bushing that we use as reference. In terms of sensors and accessory, you can have here a very easy example of the most important components of the system. Here, the bushing tap adapter. A tap adapter connects to the test tap of the transformer bushing and is suitable also for partially charged measurement and for TD tan delta measurements. This is tan delta sensor is the component that we use normally for tan delta location, tan delta measurement, sorry. And these are connected to the bushing tap adapter up to the EDS unit. And on the right, an example of UHF sensor that we use in this case connected directly to the tank of the transformer. Here, some example of sensor installation. On the left, you have a temperature sensor on the cooling oil circuit. here. In the middle, you have, you can see here an example of installation of tap adapter sensor plus the TD sensor here below. And on the right, a simple 2 gases DG8 unit. All these components are connected to the same hub, the Global Transformer Monitoring System hub. These are other example of sensor installation. This is another type of tap adapter. In this case, we have PT100 resistance and thermometers, and another type of DGA. Regarding the web server, you can have here an example of the homepage of the web server that is integrated in the EDS. This is the easy way to access to all the measurement that we can detect and we can have in our system. And we can configure this web server according to the project layout. You can see here several tabs. You have an overview with the generic information of the transformer, then main tank, cooling, for example, DGA, bushing, high voltage and low voltage side, charge arrestor, CT, CVT, and alarms. I have some other example in the following slides. Just to mention that several data protocols are available, IC61A50, 104, OPC UA, and others. Regarding other example, you can see here the representation of the main tank with several parameters and the relevant status. This is for main tank. This is for cooling. I know that probably is not so clear, but probably with the PDF of the presentation, you can have more details and more useful picture for your understanding. This is for the cooling part. And this is an example of the arms that you can have on the system. You have several lines with the value, the status in terms of presence of the yellow alarm, or in some cases red alarms. You can set and you can see also the thresholds here and the message. This is regarding the a very quick overview of the global transformer monitoring solution. We will have in the next weeks other webinars dedicated to the web interface, for example, the global transformer monitoring solution, or other dedicated session regarding the layouts and possible configuration of the system. This additional segment is related to the partial discharge testing. We have seen that during its life, the power transformer can suffer from a lot of stresses. I mean, thermal stresses, mechanical, chemical, and for sure, electrical stresses. And this stresses cause a degradation of the condition, the general condition of the transformer in terms of reduction of the electric strength, or reduction of the mechanical strength, or the thermal integrity of the windings, for example. In particular, as you can see here, thermal process can cause degradation of the cellulose through the polymerization process, or in the oil due to oxidation process or scission of polymeric chains, for example. But in this case, partial discharge can detect the thermal process or the degradation caused by the thermal process, and also with the DGA, we can have a lot of information. The same for the electrical problem that can cause a partial discharge in the paper on the press board, or other discharges in oil, and then can be detected by partial discharge. Even the localized problem in the bushing, like defect in the insulation or faulty bushing taps, can be detected. In case of bulk problems in the bushing, we normally, dielectric losses to, for example, moisture or water or bed assembling are normally detected by the TAN delta or the TAN delta system. On low tap changer, we have in some cases also arcing, and in this case with a special configuration with a special sensor, we can detect PD. Looking into the whole process, we have to detect a partially charging transformer, both for testing and for monitoring. We have to choose the right sensor, and then an acquisition unit to acquire the pulses and the waveform generated by the partially charged activity. And then we have to process all the information and make a report or have all the information inside the monitoring system. And regarding the sensor, we have seen very quickly the bushing taps. High voltage transformers are normally provided with this capacitive taps, and it represent basically a capacitive divided in parallel to the transformer. This is our favorite sensor when we have to detect partially charged not only in the bushing but also in the transformer. We have here another example. We can use also high frequency current transformer, HFCT, for example, with an installation around the ground lead of the high voltage cable that is connected to the transformer when the bushing taps are not available on the bushings. This is a real example of the installation of the UHF antenna that is normally installed in the correspondence of dielectric windows that the transformer manufacturer is able to provide in the tank. There are other type of UHF sensor. Probably the most famous one is the UHF for the oil valve. Here are the example of sensors that we also use normally in a medium voltage transformer. Basically, are coupling capacitor that are installed in parallel to the transformer bushings, or other type of high frequency current transformer installed around the ground lead of the medium voltage cable in this case, or around the cable itself when the ground lead is not available. Regarding the acquisition, you can see here an example, a schematization of the transformer with several sensors, the tap adapter, the UHF, the HFCT, and also the acoustic that are connected to an acquisition unit. In this case, you can see here on the right, our portable Altanova Aquila PD acquisition unit. This is a wide bandwidth portable unit where we can connect up to 6 sensors to have the maximum coverage, the better coverage of the partially charged detection and identification in the whole transformer. And then can be battery operated up to almost 1 day or several weeks if the portable unit is used in a temporary monitoring mode. We have, in this case, the TF-MAP technology. I will spend a couple of slides describing the TF-MAP technology also. Regarding PD, just let me do a step back for the definition of partially charged according to IC standard 60270. Basically, PD is a localized electrical discharge that only partially breach the insulation between conductors, and normally partially charged occurs in gas gaps in transformer, for example, or the insulation surfaces. One important thing to highlight is that since partially charged are related to the aging of the insulation, they can be effect or cause of the insulation, of the degradation of the insulation. On the bottom here, you can see a picture of typical representation of the acquisition of partial discharge. The name is phase resolve PD, partial discharge PRPD pattern. Is the most common way to represent the amplitude here on the vertical axis and the phase angle, the phase shift, and the horizontal axis. You can see here are also different colors. Colors are related to the intensity, to the number of pulses acquired for each cycle. And based on this pattern, defect identification can be carried out because different defect typologies have different PD pattern shapes. I have some example here. For example, on top, you have here a typical shape of internal PD, or in this case, a typical shape of a surface PD. And the third and last major category is represented by Corona PD, and you can have this typical representation of Corona PD. Identification is an important thing because, for example, internal PD are normally more and more dangerous than surface PD, and again, in general, surface PD are more and more dangerous with respect to Corona discharges. In this other example, it's not really an example, but it's a real case. We have to highlight that when we move from the labs, from the laboratory to real case, diagnosis is normally not so easy to achieve. It's not possible with standard devices. As you can see here on the graph, we have a high level of background noise, and in online tests and monitoring can be very, very hardly to have good result, because we have a very high level of background noise. And we started more or less 20 years ago to develop a method to reject the noise in such conditions in order to identify partial discharge even in online assessment. And this is our fundamental innovation of Techimp Altanova technology. So for each pulse, we calculate two different parameters through a mathematical process. Basically, we call it equivalent time and equivalent frequency. These two new parameters are used to create another representation of the partial discharge, and you can see an example here. The name of this graph is classification map of TF map. And after this process, the system is capable automatically to rebuild the pattern using only the for each cluster. So for each group of homogeneous group of points, colored in this case in black, in red, and in blue. As you can see here, using this approach, this is really useful when we have to test transformer or power transformer online, because multiple also PD sources can be identified even below the background noise level. For example, regarding power transformer, we can see here two typical PRPD pattern. On the left, you have an example of pattern for a defect due to free moving bubbles, to PD that occurs can occur in bubbles in oil, and on the right, PD that can occur in the interface between the two different layers of material, two different materials with different dielectric strength. The name of this kind of PD is interface PD. We can have many others type of PDs like corona discharge, cavities between layer of papers, for example, or also metallic particle in oil. Regarding the last part of the assessment of PD in transformer, you have here, for example, is more a short video regarding the data streaming. So basically we have the possibility to see during the measurements live the PRPD pattern, also the classification map here on the right, and even the waveforms. And for regarding this part, the processing, you can easily, also dedicate your attention to only to a specific cluster or a specific type of PD. For example, interface PD, adding filters and have also an automatic, as you can see here, probably an automatic identification of the type of PD, basically corona discharge, internal PD, or surface PD. After this operation, you can simply clicking on the report button, you can have a report of the data acquired with also the identification. Here we have seen what we can do in terms of PD test. Looking to the GTMS, our global transformer monitoring system, the GTMS exploits the time frequency analysis, so the TF map. So all these kind of activities are implemented in the software, in the central software. So you don't need to become an expert in PD analysis. All this process is performed automatically by the system. Just a quick stop. Have the third pool for you is about which is the most recommended PD sensor for a transformer. Basically, we are asking to all of you, in case of PD test or in case of PD monitoring, if the most recommended is an acoustic sensor or an antenna sensor, or for example, a tap adapter or high frequency curve transformer. Almost 50% of you already voted. A few seconds to complete the pool. 5, 4, 3, 2, 1, and we can close. Here the results. Good answer. The right one is tap adapter sensor. So more than 50% of you has response right. Then 20% high frequency curve transformer, HFCT, then antenna sensor and acoustic sensor. As I said, we prefer to use capacitive tap, the tap adapter, even though is it possible to run this test and to configure the monitoring system using also other type of sensors. Like antenna acoustic, CT, according to the layout and according to the possibility. If you have also PD sensor already installed on the transformer, for example, UHF sensor for the oil valve, this kind of sensor can be connected without problems to the portable unit if you are interested in performing only a PD test, or to the GTMS if you want to integrate this kind of sensor in the global monitoring system. Then we are ready to jump to the final segment of this webinar. So it's about a case study concerning a global monitoring results that I would like to share with you, and our experience related to this 220 kV transformer, oil field transformer, installed in Europe in this case. Just a brief prologue. Immediately after the installation of this new HV transformer, the utility start immediately to see a high level of H2, so hydrogen concentration. Then the question was, is it now necessary to take out the service of the transformer, and in other terms, why the H2 is so high? and the utility concern was about the reasons of this behavior, electrical or thermal problem. In this case, we install a temporary for a few months at the beginning, a global monitoring system. The global monitoring system composed on three parts, tan delta and partially charged sensors installed on top here, the bushing side. Then a DGA with two gases, CO and hydrogen, plus humidity and temperature. Then an acquisition unit connected to the central unit, and also dedicate human machine interface. Then after almost 1 month of monitoring, we found two different type of PD. The first one was related to gas bubbles, so PD, no so harmful PD in the oil. And the second was an interface PD. Again, interface PD is a type of discharge that due to the high electric field, radiant for sure, when you have the junction of two different materials with the two different the electric strength, for example, in the interface between air and oil or oil and paper. In this graph, I think this is very important graph because you can see here the trend over time in basically 4 weeks of the partial discharge activity. And basically you can see two different lines. One in the blue line is related to all phenomena plotted all together. For all phenomena, I mean the interface PD, the bubble PD, and some other coronas effect acquired by the system. And the red one only related to the most dangerous phenomenon. The most dangerous phenomenon in this case is the interface PD. And then you can see that in this case we have registered and recorded two big peaks, mainly due to the activity of corona and the gas bubble. And the red line is more or less stable over the 4 weeks. So this is mean that the interface PD, because this is only related to interface PD, was more or less stable among the first 4 weeks of monitoring. This is very important because, as you can see here, just to reinforce the concept, you can avoid a huge amount of false alarms that you can have if you set the threshold here. For example, if you look only on the blue line, you have a lot of coronas and other type of PD. Let me say, due to the big amplitude of this phenomena that are not dangerous for the system. So after this first period, the utility decided to perform an oil treatment, and was for sure carry out in a couple of days. And the first activity disappear. The first activity we recorded due to the gas, to the PD in bubbles disappear after this treatment. And the second one, the interface PD, immediately appeared again. So in this case, the oil treatment did not cause any benefits in reducing this kind of phenomenon. And for this reason, the utility decided to extend for other 6 months the period of the installation of the monitoring system. And you can see here other results for a 6 month of monitoring regarding the tan delta. And this line was almost stable. The capacitance value also was stable. And for the DG8, we during this period, during this 6 month, we have seen almost 30 ppm per day of increase of the concentration of the hydrogen detected by the DGA. Here the parts relevant to PD. Again, this is the trends only related to the most dangerous PD in the transformer, in this case, the interface PD. So PD in this case were detected for all the three phases, such demonstrating that was this kind of PD was directly connected to the also the increase of the H2 value. So after this additional 6 months of monitoring results, the diagnosis was the following. So 3 different PD activities inside the transformer, one for each phase. Such PD activities were the cause of the increase of the H2. We also detected high frequency counted the PD. That means that was very close to the upper part of the transformer. It identifies as an interface phenomenon between different dielectric materials with a stable trend over the time. The conclusion was that PD was possibly generated at the 3 interface between air and oil in the 3 domes just below the bushings. This is due normally to the not perfect filling of the transformer in the interface air and oil. Just to complete the result of this study and this experience, you can see here a comparison between the test performed offline and the result performed and acquired and calculated, let me say, by the monitoring system. This step was a specific request for the utility, was exactly carried out to be 100% sure that the PD detected by our system was not relevant to external interference, for example. And you can see here in the comparison that all the values were confirmed between the online result and following offline result. For your reference, you can see also the RPD detected during the offline test. Just to close this experience, the utility decided to drain it and degases the transformer, and then it was filled up again, in this case with some dedicated procedure with hot oil and in a very precise manner, let me say. And the transformer was, after these activities, was put on service again, and with the monitoring system installed. These are the results after the actions performed by the utility. You can see that transformer was now completely PD free. No other increase of H2 was recorded by the DGA unit. And then you can see also that from this RPD that only noise is present. So we also eliminate any interface problem with the interface in air and oil. So the conclusion of this experience was very, let me say, positive for the end user and also for us. We reach a sensitivity also comparable with the offline test. It is very important, this point. And also this kind of approach, or I mean, the real-time and online global monitoring system benefit has been fully proven with this kind of activity. This is our last pool. We are close to the end of this webinar. I kindly ask you to answer also to our last question regarding the strategies. So what strategy are you considering for the future for your transformer? To use time-based maintenance, to repair after a fault, to use a global monitoring system or monitoring system in general in terms of implementing predictive maintenance strategies. I can see 60% of you already voted. Few seconds. 5, 4, 3, 2, 1. we can close the pool and share the results. We can see that almost 90% of you we use predictive maintenance. Only 5% have intention to repair after a fault. Almost 20% to use time-based maintenance. Let me hide the results. I can see that these results are more or less aligned, and also in this case with let me say, a growing trend to a more holistic approach on the transformer management, on transformer fleet management. Even compared with the past, we can see a really growing number of operators that are moving from TBM to CBM strategies. And this is really important. We start our presentation discussing about strategies to increase profitability, reliability, and safety. And you can see here some of these advantages to increase, for example, in reducing the manual rounds, to have lower maintenance costs. Let me say that in general, thanks to global monitoring system and solution, GTMS, for example, we can have for sure a better visibility of the status of the transformer and a better understanding of the risk. And these are, as I said, the key factor to improve the mitigation strategies and give it for sure also less concern to all of you regarding the status of the transformer, and in general less concern to all the transformers operators. This was my last slide for today. I would like to thank you so much for your attention, and I think that we can have few minutes to read some of your question and try to reply also to your question with also my colleague Mirko, and you can see here also my direct contacts. You can reach me by email whenever you want. If you have any doubts, if you have to receive also a better picture describing the system, I realized during the presentation that the font and also the dimension was not so exciting, quite difficult to understand. Please don't hesitate to reach me to have a copy or high resolution picture also in this case. Thanks again for your attention, Mirko. If you have any interesting question that you would like to share with all of us, we will try to also to answer to these questions.
Hello to everybody. Well, actually, there were unexpectedly only few questions. I don't know if there are some more. I've responded in a written manner to the question, but not many technical questions indeed.
Okay. Do you would like to read a couple of them just for the audience, or?
Well, there is, I see another question here regarding the tap adapters. Are the tap adapters universal to any manufacturer bushings? Unfortunately not. There are specific thread type for that has been chosen by the bushing manufacturers. So, for example, ABB, just to mention one, they have plenty of different types. And some others are stick to a single type, like Trench, which is using always the same. In the US market, it's quite common, the IEEE thread. But in general, no. In general, we have to know the bushing type and possibly the drawing of the test tap in order to choose the right tap adapters, which is well, probably already in our archive, but there are many tens of different types.
Good, thank you. I can see also another interesting question. How many hours, days in outage will be required to install all the devices of an existing transformer? You already answered to this question,
Yeah,
and I
right.
think that we can also
Yes.
share this with all the audience.
Yes, we usually takes about 4 or 5 days the installation. But for the outage, a couple of days are usually enough. You know, when you have to climb up on the roof of the transformer to install the tap adapters, then most of the work is carried out on the ground, let me say, on the side of the transformer. Then I see another question regarding the UHF sensors. How many UHF sensors are required to cover the entire power transformer? In most of the cases, 3 sensors are sufficient, but let me say between 3 and 6. Ideally, 6 sensors on 3 on both sides of the transformer will ensure, let's say, the perfect cover of the transformer. But the minimum is 3, and in most of the cases, it is enough. Then I see on this subject another question: the main difference between UHF used in GIS and transformer. Well, basically the same frequency range is used. Maybe in the GIS, the bandwidth is stressed up to 2 gigahertz. In the transformer, probably is not necessary to have such large bandwidth. But we are proposing the same sensors for both, for the GIS monitoring and for transformer monitoring. In the transformer monitoring, of course, you have to rely upon a dielectric window to seal the oil and keep, of course, the pressure of the oil inside the tank.
Thank you, Mirko. I think that we can have probably 1 minute to answer to the last question. I think one of the most interesting one is how to address corona impact from outside the overhead line while using bushing tap sensor. So if you can.
Yes, well, this is one of the let's say relatively easier let's say noise rejection that we can found. The corona is present in most of the installation. It's coming from the overhead line, as you are aware of, and it can be easily filtered thanks to the TF map. So again, thanks to the software filtering, in particular thanks to the TF map, we can easily reject the corona and a specific domain of the map from the acquisition.
Excellent.
Then, so I think that we are over.
Yeah.
There are some other questions. Maybe we can respond in writing.
We can respond in writing, and we can also respond in the next days if you can use our contact to make other questions to me, to Mirko, to other colleagues in the team. We are more than willing to reply to all of you. Yep. Thanks, Mirko, also for your support, and thanks for everyone for being with us today, and hope to see you for our next webinar. Thanks again. Bye-bye.
Bye-bye.